So today we're going to discuss partial derivatives. So let's start with a quick recap of what we saw in the flipped class video. So let's start with a picture. So suppose I have some surface in 3 space. So let's get a surface here. So maybe my surface looks something like this. And this is my z is equal to f of xy. And suppose we pick some point here. So this is x0, y0, 0, so it's in the xy plane. So if we look up, we'll have some point here, and this point would be x0, y0, f of x0, y0. And what I can ask is, suppose I want to look at and fix y0 and just let the x vary. So if I did that, my x is varying, my y is fixed, so it's going to look something like this, going through this point. So this would be z is equal to f of x, but then we're going to fix y0. And so I might be interested in if I have a function of more than one variable, how does that function change if I'm changing only one variable? So we can ask, how does f change if we only change x? So in that case, we can look at this picture and we could ask, well, if I'm only changing the x, I could ask for what is the slope of this tangent line to that curve, that orange curve. And so that's how we went about our partial derivative. So we define this as delta f delta x. So these are curvy d's now at the point x0, y0. You could also use it with a subscript x. And this is the limit as h goes to 0 of f of x0 plus h y0 minus f of x0 y0 over h. So we can see it's essentially the same formula as we used for the derivative. It's just we have two variables now and we're only letting one of them change. And we can do, of course, the same thing with y, where we fix x and just let y change. And so then we can use a subscript y there. And then this one will let just the y value change. And this would have the same meaning in terms of the geometry, where now we would fix the x and we would have the slope of the tangent line to a curve where y is changing and x is fixed. So that's a quick recap of our flipped class video. So now let's go about seeing how this shows up in some examples. Okay, so we have a thin metal plate. We're going to have this line in the xy plane. We'll say its lower left corner is at the origin. So the temperature at a point, say xy, given in degrees Celsius, is, we'll say, T of xy. And so we're going to give this in terms of a table. So first let's just get an idea of what's going on in terms of a picture of our plate. So this will be x, say y, and this is our plate here. So if I want the temperature at some particular point, say I go over here and this is like, say at 2, 1, over down here, remember this is at the origin. So the temperature here is T of 2, 1. And now we're going to say our temperature is given by a table. So let's say temp in degrees Celsius. And so let's make our table here. So let's say my x values go along here. So these are x, and then the y values go along here. So these are y values here, and these are in, say, meters. And then let's just go ahead and fill these in. So this says 120, 125, 185, and then let's go 135, 128, 110, 90. Let's say that's still 160 there. Let's call this one 150, and then 175, 190, 155, and let's say 160, 170, 180. Okay, so that's our values for our temperature. Now let's say suppose we fix y equals to 1. So we're only interested in the row where y is equal to 1 right now. And let's let x vary. So then we could set f of x to be t of x1. And so we could ask, what does f prime of, say, 2 mean? Okay. So what this is telling us then, since we've fixed our y to be 1, this is asking us how the temperature changes as we move away from 2 in the x direction. So right, so if we're thinking of our picture before, where we were over at 2, 1, let's say 2, 1, and we're at this point, this is telling us how does the temperature change as we move in those directions. So what we saw is if we think of our formulas here, well, f prime of 2, right, this is the partial derivative at 2, 1 of tx. So we can think of this in two ways. Let's think of it this way first. Let's think of, well, this is the limit as h goes to 0 of f of 2 plus h minus f of 2 over h. And then if we fill that in with our formula, this is t of 2 plus h comma 1 minus t of 2 comma 1 over h. And we see that's exactly the formula for the partial derivative of t at 2 comma 1. And so now we can estimate this using our table. So tx of 2, 1, well, this is approximate. If we look here on our table and we go to 2, 1, so we're 2 in the x direction, so this one, and 1 in the y direction, so we're right here. And then we want to change our x's, so we could go to this one, or we could go to this one. So this would be, say, we could say this is approximately t of, say, 3, 1 minus t of 2, 1 over 3 minus 2, which is 160 minus 135 over 1, so about 25 degrees Celsius per meter. And one thing we can note from this is that since this is positive, that means the temperature increases is we move to the right from 2, 1. Okay, let's try another example. This one we'll use a contour plot to estimate. Okay, so there's our axes, and let's put some contours on this. So something like this. Okay, and we'll say this is, say z equals 1. Say this is z equals 2, z equals 4, z equals 7, and z equals 9. Okay, and we'll say x and y are measured in kilometers. Okay, and the heights of the topographical map, so the z's, are measured in kilometers. Okay, so let's say so let's let h of xy be the height function given by the contour plot. Right, so z is equal to h of xy. So what do we want to do with this? Let's estimate hx of 1, 1 and hy of 4, 3. And now we're not going to be able to tell this exactly from the contours clearly, but we're going to try to estimate this just looking at the picture. So what we're going to do is we're going to go to 1, 1. So if I'm at 1, 1, I'm about right there. So that means h of 1, 1 is about 4. And then we want to move in the x direction by 1. So if we do that, we're about right here. And so we're going to have to estimate that. That's somewhere, if I was thinking of how these contours are shaped, it's kind of between these two contours. So between 4 and 7. So let's go ahead and estimate that at about 5.5. So we can estimate hx of 1, 1 is approximately h of 2, 1 minus h of 1, 1 over 2 minus 1. So this is approximately 5.5 minus 4 over 1, so about 1.5. And this would be in kilometers per kilometer. So that means if we move to the right, if we're standing at 1, 1 and we walk 1 kilometer to the right, we're going to increase our height by about 1.5 kilometers. So if Okay, and so our next one we want to do is for 4 and 3. So if I go to 4 and I go up to 3, I'm about right, let's say about right there actually. So that's about halfway between 7 and 9. So let's estimate that at 8. And then we want to increase this by 1. So that would be about right here. So that's about 2/3 of the way between 4 and 7. So let's estimate that at 6. So that means h of y at 4, 3 is approximately h of 4, 4 minus h of 4, 3 over 4 minus 3, which is approximately, we're going to say 6 minus 8 over 1, so 2 kilometers per kilometer, negative 2 kilometers per kilometer. So this means if we are standing at 4, 3, and we walk, say, north 1 kilometer, our elevation will decrease by about 2 kilometers. Okay, let's try another example. Let's consider the following function. So I'm going to try to draw this. Something like this. Okay, so let's look at this point here, and let's say this point is 0, 5, 3. This is z of f of x, y. So we can look at these two things like this. And let's ask ourselves the following questions. Okay, so what is the sign of the partial derivative of x with respect, or the partial derivative of x at 0, 5? Well, what we want to think of here is if we're at this point on our graph, so suppose we're right here, what we want to say is if I'm changing in the x direction, so if I'm walking towards the positive x direction here, am I going up or down? Well, we can see by the curve of this function here like this, I'll be going down. So if we move in the positive x direction, f of x, and then we're going to leave the y fixed, decreases. So that means f of x at 0, 5 is negative. You can think of, remember, this f sub x of 0, 5 is the slope of the tangent line there. And so the tangent line there is going to have a negative slope. Now, what about in the y direction? So we can ask the same thing. what is the sign of f of y 0, 5? Well, in this case, it looks like if we were to walk to the positive direction for y, we're going like this. It looks like we're going up. So this one, f of y of 0, 5, should be positive. Okay, so now that we have a kind of an understanding of what the partial derivative is and what it's telling us, let's go ahead and do some calculations. Make sure we know how to actually calculate the partial derivatives. So let's take the partial derivative of 1 over a of e to the minus x squared over a squared with respect to x and with respect to a. So when we do these, we treat the other variable as a constant. So for the first one, I'm treating the a as a constant. So just think of it as just a number. And you're just taking the derivative of this function with respect to x. So that means the 1 over a stays the same. And now I'm taking the derivative of e to the minus x squared over a. So that's e to the minus x squared over a again. And then chain rule says we need the derivative of what's inside. Since the a is a constant for this calculation, this just becomes minus 2x over a squared. So if we want to simplify this a bit, this is minus 2x over a cubed e to the minus x squared over a squared. And now, same idea when we take the partial with respect to a, except for now we're treating x as a constant and a is the variable. So we need to use product rule for this. So it's the derivative of the first, which is going to be minus 1 over a squared times the second, plus the first times the derivative of the second. And now remember, this prime is with the derivative with respect to a. So this is minus 1 over a squared e to the minus x squared a squared plus 1 over a e to the minus x squared over a squared. And now I have the negative there, but now I'm going to get, and I'll leave the negative x squared there. And the derivative of 1 over a squared is minus 2 over a cubed. So this becomes minus 1 over a squared e to the minus x squared over a squared plus 1 over a e to the minus x squared over a squared. Now those two negatives cancel and I get 2x squared over a cubed. And so I can factor this a bit. I can bring e to the minus x squared over a squared out front. I can bring in 1 over a squared out front. And then what I'll be left with is 2x squared. And then if I take a squared out of that, I have a squared left. And then I've subtracted everything out of the other one. Okay, let's try a word problem here. Okay, so suppose we have money in a bank account. We're going to say it's earning interest at a continuous rate of r. let's say the amount of money, which we'll call B, okay, so the amount of money we have in the account, which we'll call B, depends on the amount deposited, which we'll say is P, and the time it's been in the account, T. And this is according to the formula B is equal to P e to the RT. Okay, so let's find delta B delta P and delta B delta T and interpret them financially. So what are they telling us about the money in the account? So delta B delta P, notice everything in there is a constant except for P, so this is just e to the RT, which we can think of. We could also rewrite this as B over P. And if I look at delta B delta T, this is P, and then I'm going to get e to the RT back times R, which is R times B. Okay, so both of these are positive. So they both tell us that B increases if we increase P or T. Okay, finally, let's do one last example, and we'll do this one from physics. Okay, so we have this formula here. We know c is equal to the speed of light. V is bigger than or equal to 0 and less than c. So you might have seen the formula before, E equals mc squared. Notice that's the formula we get here. Yeah, so this is just a more exact version of that formula. Okay, so what are we going to do with this formula? So let's do a couple calculations. Let's find delta E, delta M, and then what? Okay, so a couple calculations here and then thinking about what these things mean. So let's start with delta E, delta M. So in this case, if we look at this formula up here, the M appears very easily. It's just right here, and everything else is a constant. So that makes that derivative particularly easy to do. This is just going to be c squared, and then I'm going to have 1 over the square root of 1 minus v squared over c squared, minus 1. And so now, for the sign of this, note that v squared over c squared is less than 1, because v is less than c. So that means 1 minus v squared over c squared is positive, and 1 minus v squared over c squared is less than 1. So that means 0 is less than the square root of 1 minus v squared over c squared, which is less than 1. So if we divide by something less than 1, we get something positive. So 1 over square root of 1 minus v squared over c squared. This is going to get even bigger, so this is bigger than 1. So think of, if it isn't clear, just think, well, if this is between 0 and 1, think of it as being like 1/2. Well, if I divide 1 by 1/2, I get 2, which is bigger than 1. So in particular, if this is bigger than 1, then I have something bigger than 1 subtracting 1, so this is positive. So delta M, for delta E, delta M is bigger than 0. So what does this mean? So this means increasing the mass of an object increases its energy. Okay, and I think you can imagine that making sense. If you throw a ball and you're getting hit by like a dodgeball or something, if you throw two different dodgeballs at the same speed, the more massive one's going to have more energy when it hits you. Okay, for the second one, let's rewrite this equation to save us a little bit of effort. So remember, this is mc squared over 1 over square root of 1 minus v squared over c squared minus 1, which is, say, mc squared, and then I'm going to write this as 1 minus v squared over c squared to the minus 1/2 minus mc squared. And now the only thing that's changing here when we take with respect to v is just this term here. So that means delta E, delta V, I'm going to get mc squared, and now I have to use chain rule on this. So first we use the product power rules to bring this down. This becomes minus 3/2, and then the derivative of what's inside is going to be minus 2v over c squared, and then the minus mc squared is a constant, so that just goes away, it becomes 0. So notice the c squareds cancel, so this just becomes minus 2mv, well, and then the 2 and then minus, so let's maybe be a little careful here when we're crossing things out. So let's say, so I have the c squared here and the c squared here, and those cancel. And then I've got the minus 2 here and the minus 1/2 here, so those cancel. So this just becomes mv, and then I've got 1 minus v squared over c squared to the minus 3/2. Which, if we want to rewrite, this is mv over 1 minus v squared over c squared to the 3/2. And we can see everything here is positive because we saw above that 1 minus v squared over c squared is positive. So this is positive. So as we increase the velocity, so does the energy. And continuing with the dodgeball reference, if two dodgeballs of the same mass are thrown at you and one of them is going faster, it has more energy when it hits you.